So ice tables you can use, and this is really important to memorize. Well, I have them in my nifty little ice table. I hope that helps. They're very powerful, and it's just a nice, neat way of keeping your concentrations or pressures in order so that you can actually solve a problem. I don't want you to be afraid of them. I want you to embrace them. And I want to show you two problems, and these are examples of problems that you can solve using an ICE diagram. First of all, what does ICE stand for? It stands for Initial, Change, and Equilibrium. And we're going to set up a little table. And the first thing you need to know is what kind of units can you use? So ICE tables you can use, and this is really important to memorize, you can do them in molarity, or moles, or pressure units. Okay, so maybe atmospheres or something like that. So this one I'm going to choose to use molarity because that's what's given in the problem. So work with me on this one. So I've got a reaction at equilibrium, and I know the initial concentration of the N2O4 is 0.100. I'm not going to use my unit there, but I'm going to put molarity just to remind myself that this whole table is in molarity. So I've got to have all the same units there. If I do moles, I have to be moles. Okay, so then there is no NO2. So when I start off, I'm all product. What's going to begin to happen? That N2O4 is going to react and turn into NO2. And so we're going to lose N2O4 and gain some NO2. Now the other piece given is that the N2O4 at equilibrium is 0.009. So I'm going to write that in my table. So at equilibrium, 009. Now the middle row is for change. What is the change? What has happened? Well, we went from 0.1 to 0.009. So the change is, you subtract the two, we went down by 0.091. Now, when the N2O4 goes down by 0.091, what happens? We created some NO2s. And how much? Well, we created 2 times that. So I'm going to say plus 2 times 0.091. Because look at the coefficients. We've got 2 NO2s for every 1 N2O4. So we produced that concentration. So at equilibrium, what happens? Well, we went from 0 NO2, we added 0.182. So the ICE table is just to get to those equilibrium concentrations. Now, Kc, we're going to calculate Kc. I've got an equilibrium constant expression here, so N2O4 over NO2. Now, these are both gases, I know that, so I'm including them in the expression. So I've got the expression. Now what I need to do is plug in the equilibrium concentrations. Well, I have them in my nifty little ICE table. So all I need to do is take my equilibrium concentrations and plug them into the expression. So for the N2O4, I have 0.009, and then on the bottom I've got that 0.182, and I will square that. Okay, let the calculator do the work, and you get 0.272. So we found the equilibrium constant for this equilibrium. Now let's look at another problem where we can use this ICE table. So same reaction. This time I want to find the concentration of N2O4 at equilibrium. So I'm looking for this box. All right, so let's see what's given. Well, I've got the Kp. What is Kp? Well, Kp is an equilibrium constant, but we're just dealing with pressure, and so I'll write it in terms of pressure. So it's the partial pressure of N2O4 over the partial pressure of NO2 squared. Okay, so it looks just like a Kc, but we're using partial pressures. So I've got that, and then let's see what else we have. Initially, we only have atmospheres of NO2. So I've got 3, and I'm going to put my unit over here, atmospheres. So I want to stay in pressure units. And I have none of that. So what happens? Well, initially, all we have is reactant, so we're going to start making some product. let's use our X trick again. Let's say that since I'm going to be looking for that partial pressure of the N2O4, let's make that X. So that is going to be my X right there. And how do I get that? Well, if X is the partial pressure of N2O4, where did it come from? Well, I'm going to lose 2X of my NO2 because of those coefficients, right? 2 and 1. And so at equilibrium, I'll have 3 minus 2X, and at equilibrium, I'll have X. Now, let's go plug these values in to our Kp expression. So Kp, which I know is 9.3, 10 to the minus 7th. Okay, there's my Kp given in the problem. Partial pressure, this will be X, and on the bottom I have 3 minus 2X, and that whole thing is squared. And when you look at this, you may say, oh no, I don't want to use a quadratic equation. I recognize I'll have an X squared term and an X term, and that's a mess. Well, often in these problems, because I know that this value is so small, that 2X is what we call negligible, okay? So in other words, 3 minus 2 times a tiny, tiny number is approximately 3. And so because of that, we can assume that that little term is negligible. You can't always do that, but in this case we can. Well, this simplifies things. So this now is equal to X over 3 squared, which is 9. And so X in this case is going to be equal to 8.4 10 to the minus 6 atmospheres. And what was X? It was that partial pressure of N2O4. So it's a very, very small value. And that's just another example of how to use an ice table. Remember, units can be molarity, moles, or pressure units. I hope that helps. They're very powerful, and it's just a nice, neat way of keeping your concentrations or pressures in order so that you can actually solve a problem.